You know all those numbers you see on food and drink labels? Ever wonder what they really mean? Well, today we're going to crack the code on one of them, pH. We're going to take a simple number and unravel this fascinating story about the hidden math and chemistry that's literally all around us every single day.
Okay, let's just dive right in. So you might see something like this on a bottle of water, pH greater than 8.8. Now most of us kind of know that pH has something to do with acidity, right? And that 7 is neutral. But 8.8? What does that actually mean? What's the story that this little number is trying to tell us?
And yeah, that's really the big question here. I mean, 8.8, it doesn't seem that far off from 7, does it? The difference is just 1.8. But as you're about to find out, when it comes to pH, those small numbers can be super deceiving. So think of this as a little math literacy challenge, and I promise you, the answer is way more dramatic than you might think. So to crack this code, first we've got to learn the language it's written in, and that language is logarithms. Now, I know what you're thinking, but don't worry, we are going to keep this super simple. Seriously. Logarithms are just a really clever way to deal with numbers that are either huge or teeny tiny and kind of wrangle them into something more manageable.
And here is the absolute core idea. A logarithm, or just log for short, it's not a thing, it's a question. That's it. When you see log of a number, all it's asking you is this: 10 to the power of what gives me that number?
Okay, let's try an easy one. What's the log of 100? Remember the question, 10 to what power gives me 100? Well, that's 10 times 10, right? Or 10 squared. 10 to the power of 2. So the log of 100 is 2. See? That's all it is. You're already doing it. Okay, how about the log of 10? Same question. What power of 10 gives you 10? Well, that's just 10 to the power of 1. So the log of 10 is 1. Easy enough, right? For these bigger numbers, it's almost like you're just counting the zeros.
All right, but now, this is where it gets really useful, especially for chemistry. What about a small number? What's the log of 0.1? So what power of 10 gives you 0.1? The answer is a negative power. It's 10 to the power of -1. So the log of 0.1 is -1. And this right here, this ability to handle these tiny little fractions, is exactly why logarithms are perfect for talking about pH.
And just a quick side note here. We've been using base 10 for all these examples. That's the most common one, but you should know that other bases do exist. Using base 10 is really just a choice scientists made, so everyone is speaking the same language. It's all about clear communication. Okay, so we've got the language down, we understand logs. Now it is time to put it to work. Let's use what we know to finally crack the pH code.
And here it is. This is the key to the whole shebang. The P in pH, it stands for potential of hydrogen. But really, that little p is just an instruction. It tells us to do one thing: take the negative log. So a pH of 7 doesn't just mean 7. It means the negative log of the hydrogen ion concentration is 7.
So if you remember one thing, remember this. A pH value, it's just telling you the power of 10 for the hydrogen ion level, but with a minus sign slapped on the front. That's it. So when you see a pH of 7, what it's really saying is that the concentration is 10 to the power of -7. That's the secret. That's the code.
Now you might see this unit here, mole/L, moles per liter. Don't let that throw you off, okay? A mole sounds weird, but it's just a word chemists use, kind of like a dozen for eggs, but for a ridiculously huge number of atoms or ions. It's just a standard way to count a massive amount of really tiny things.
All right, the moment of truth has arrived. We've learned the language, we've learned the code. Let's go all the way back to that water bottle and finally reveal what that small difference on the label actually means in the real world. So let's ask our original question one more time. Is a pH of 8.8 really just a little bit different than neutral water at pH 7? The difference on the scale is only 1.8. So is it a big deal or not?
Okay, let's look at the math. It's simpler than you think. Neutral water, pH 7, has an ion concentration of 10 to the -7. Our bottled water, pH 8.8, has a concentration of 10 to the -8.8. Now, to see how many times different they are, we just have to find the ratio. We divide them. And when you divide powers of 10, you just subtract the exponents. So, -7 minus -8.8, that gives you positive 1.8. The difference is 10 to the power of 1.8.
So, what is 10 to the power of 1.8? Drumroll, please. It's about 63. Yeah, 63. That water with a pH of 8.8 has 63 times fewer hydrogen ions than neutral water. So that tiny, innocent-looking 1.8 difference on the label, it's actually a massive 63-fold change in the water's chemistry. No way is that a small difference. Not at all.
Okay, so why does this matter? Who cares, right? Well, it matters because this isn't just some fun party trick with a water bottle. This hidden math, this code, it shows up in so many parts of our daily lives, and a lot of the time, the consequences are super important.
I mean it. This stuff is everywhere. We're talking about the water quality in the swimming pool you jump into, the soil in your garden that needs to be just right for your plants to grow, keeping the fish in your aquarium happy and healthy, even getting that perfect tangy crunch when you're making pickles. All of it comes down to understanding this logarithmic pH scale. It's critical for safety, for health, and hey, even for flavor.
And that, right there, is the big takeaway. A small change on the pH scale is a huge change in the real world. A single point difference, like going from a pH of 7 down to 6, that's not a small step. It's a 10 times leap in the actual acidity. That's why those little numbers on your pool testing kit or your gardening soil report are so important. So from now on, when you see a pH value, you're not just going to see a number, are you? You're going to see a story written in the language of logarithms. Because we've seen today that sometimes the simplest numbers can tell the biggest, most surprising stories. You just have to know how to read the code. Makes you wonder, right? What other codes are out there, hiding in plain sight,